Symmetry.
Okay. We start by thanking the organizers, Surat and Vishnu, particularly Vishnu for taking the initiative, arranging everything here. So today I'm going to talk about a particular type of local unity invariant with multipartite states that we call multi-invariant. Multi-invariants, a class of such things called multi-invariants, and bulk replica symmetry. So what I mean by bulk replica symmetry will become clear in the course of the talk. So mainly we want to ask questions about multipartite properties of a holographic state. Multipartite entanglement properties of a holographic state. So I have to tell you first what I mean by holographic state. So before that, let us just consider a conformal theory with large central charge and large gap, and radius CFT correspondence tells us that it is dual to a gravitational bulk, one higher dimensional gravitational theory. The dual in the sense that if you want to compute a partition function of the CFT on some manifold M, it is calculated at a leading order in N by the action of the gravitational action of the leading saddle point that fills in this bounded manifold M. So this is we would need radius CFT duality at this level. That the partition function is given by the action of the gravitational saddle that fills in the geometry. Okay, so this is what I mean by a holographic theory, and this holographic state is a state in this theory which is described by a gravitational bulk geometry, by a bulk geometry as opposed to superpositions of geometries, for example. So the canonical example of such a thing is vacuum state entropy, CFT, which is described by the vacuum state itself. We can construct by performing a path integral on a hemisphere to write down a state on the equator, and this state would be described in the bulk by filling this out in a hyperbolic dimension. Some of the other examples include a heavy operator acting on the vacuum state into the CFT, so that it is approximated by a geodesic that passes through the bulk. Thermofluid double could also be thought of as a state which admits a gravitational interpretation and hence is holographic. Okay, so but in the rest of the talk, we will stick to two-dimensional CFTs, and in particular their vacuum state, to ask our questions about multipartite entanglement. So what do I mean when I say that the vacuum is a multipartite state? You take the vacuum state, which is defined on a circle, and you divide the circle into multiple regions. Here I have divided into 3 regions, and for a division of the boundary, division of this spatial circle into multiple regions, you can associate factors of Hilbert spaces. And in this way, the entire Hilbert space, you can think of it as being factorized into multiple components, each associated to a given region. So you have A, B, C, you have the Hilbert space factorized in terms of HA, times HP, times HC. And we are interested in the properties of this state thought of as a multipartite state, meaning we are interested in characterizing the properties of the state up to local linear transformations in A, B, and C. Okay. In particular, we are interested in asking the question, what makes the state, what makes the holographic state holographic? Meaning, does it have any special properties compared to a generic multipartite state? Okay. So, in order to explore this question, we have to figure out what are the appropriate multipartite invariants, meaning multipartite local unitary invariants that we should compute in order to probe this question. So we demand that those multipartite invariants admit a convenient geometric description. So what do I mean by a convenient geometric description? Well, let me explain that with the help of an example. So we are all familiar with, in the bipartite setup, that the state is bipartite. We talk about trace of rho to the n as input to any entropy, and from there n going to one limit will give us the one limit entropy, rectangular entropy. but in this talk I will not be necessarily interested in taking n going to 1. Let's just work at a finite n. So let's consider this trace over n for a bipartite state. So for the bipartite state, we just have two regions, A and B. And we know that it is computed by, if you don't know, I will give you this, but let's for now, let's just take this, that it's evaluated by action of an orbifold geometry. So you have a hemisphere, it is capped off by another hemisphere, because this is bra, this is get. So on the boundary you have a sphere, and it is filled in by the bulk solution, but it's not a smooth bulk solution. It is topologically a ball, but geometrically it has a singularity with a cone angle 2 pi by n that stretches from the one endpoint of this region to another endpoint of the region. Okay? So this is what I call a convenient geometric distribution, because it is given by a geometry that is topologically a ball, but with certain singularities that stretch out in the bulk and finally end up meeting the boundary points of the regions of interest. Okay? So you want to find other multipartite invariants which have this property. So we will formulate this more precisely later on, but this is what I mean by convenient geometric distribution. So let's see how it comes about in the bipartite case. You have this bipartite state, psi ij, and you take multiple copies of this state, n copies of this state. So you have n copies of psi ij, so I have denoted them as psi i1j1 all the way up to psi in.jn. I is an index for the first party, j is an index for the other party. The subscript of the indices refer to which replica we are talking about. And these are bras if you wish, then we also have gets, and they also are labeled in this way. So, in order to compute trace over n, we contract the party one index, party A index with party A index. So if you consider this contraction psi with this psi, you get I1 I1 contraction, and you get a row with the indices J1 and J2. Similarly, you get a row with the indices J2 and J3, and so on. And this product then and the sum engineers trace over n. Okay, and it's very clear what to do on the quantum field theory side if you want to compute this quantity. As I said, psi's correspond to the path integral on the southern hemisphere, giving you the graph, and psi bar corresponds to path integral of the northern hemisphere, giving you your get. And this indices that you're contracting of the party A first, that just means that you are just moving along the party A, but party B I have not included, so there's a slit open at the party B. Similarly for all, so each of these spheres with a slit, you should think of them as a row, and then you're taking product, successive product of rows, and then taking the trace that corresponds to gluing the top edge of this to the bottom edge of this, the top edge of this to the bottom of this, and so on in a cyclic way back to the first copy. The top edge of the last one goes to the bottom of the first one. Okay? So in this way, you construct a new space. Okay, in this case, a boring space, because topologically it's just a sphere again. You can see that, but it has at these 2 points, these 2 interesting points, it has a conical axis of angle 2 pi n. Okay, so it just goes round and round and round and comes back after 2 pi n angle. And move the poles if you wish. You can take for simplicity these two to be the poles of the sphere. Okay. So this, this invariant then is given by the partial function of the CFT on this space. Now this space is a funny space as I mentioned, but because we are in 2 dimensions, you can always write down a metric which is y equivalent to this one and which has constant negative curvature, well, constant curvature. So in this case, you can uniformize this to a round sphere. You can do away with these singularities at the cost of a single y factor. Now this helps us write the partial function of this as being product of a contribution coming from the y factor and the partial function of the round sphere. But this particular way of computing the partial function is not going to be terribly useful for us. We will stick to this replicating space. Okay? We will only consider the uniformized geometry for certain mathematical analysis in order to see how the symmetries are acting, because the symmetry will play an important role later on. So, but in order to compute the partial futuristic with this space, with the conical axis. But at the back of our mind, we should keep in mind that such a space is widely equivalent to a subspace. So in this case, this boundary manifold M that we have constructed by gluing n copies of the sphere around each other clearly has a Zn replica symmetry. Zn symmetry that we call the replica symmetry. And also that according to CFT, as a area CFT correspondence, as I said, the partition function of this space is computed by the gravitational solution B that fills in this sphere. So the boundary manifold that I get after doing this procedure, I will always denote that by M, and the gravitational solution that fills it in, the leading gravitational solution that fills it in, I will call that curly B. So we have this equality from area CFT correspondence that partition function here is equal to weight minus S cap on curly B. Now in this case, the Zn replica symmetry of the boundary also extends into the bulk. This is easy to see. So we can go ahead and quotient the whole bulk geometry by the Zn action. So after quotienting, we get on the boundary was a sphere replicated n times, that's why we had conical axes of 2 points with conical angle 2 pi n. But after quotienting, all that excess goes away and you just get the original boundary that you had started off with, which was just a sphere. And moreover, the bulk, which was smooth to begin with, has a locus which is fixed under Zn symmetry, and because of this quotienting, it will introduce a singularity with conical angle pi by n, which starts at one point at one pole and ends at the other pole. So that's the picture we get. That's the orbifold P tilde that we get. So when the replica symmetry, when we quotient the bulk solution B by the replica symmetry, the orbifold that I get, that I will denote by this little curly P tilde. Okay? And because we are quotienting, what we are computing is not quite trace root Vn, but 1 over nth power of trace root Vn. So if you wish, this is a normalized invariant, because I started off with n copies of the state and finally I'm taking a 1 over nth power. So in fact, all the invariants that will be constructed in, that I will be interested in, will have this property. They will all be normalized. So I will construct them using multiple copies, but finally I will take a n through so that it is an invariant per copy if you wish. So this then gives me a normalized invariant E, and now this is given by the gravitational action of the quotient space, the orbifold space. Okay, because B, as far as the action is concerned, is simply taking B tilde n times. So this equality holds. Okay, so in this way I can compute this normalized invariant as the gravitational action of the orbifold singularity. Okay. So from this analysis, we brought two lessons. That what we are interested in are multipartite invariants that admit a similar type of description, meaning that it should be computed by an orbifold geometry first, whose boundary is the original sphere. Okay, that's the kind of condition that we want our invariants to obey. And inside, topologically, it is the same as the ball, but it has some conical singularities. That's the kind of solution that we are interested in. So for that, two conditions must hold. First is that the replica symmetry R must act freely and transitively on all the replicas. Okay, so that we can quotient the boundary itself, so that the boundary goes back to being the original sphere. That's condition one. It turns out it's an algebraic condition and can be easily solved for any replica symmetry R. I will tell you how that works. The second, more non-trivial condition is that once you construct this replicated manifold M, meaning you start with a sphere, northern hemisphere and southern hemisphere, take a bunch of copies, and you will glue them in a particular way, as I will describe soon. And the manifold that you get at the end of the day, which was the sphere with 2 pi and vertical axis in the previous case, that manifold M, that manifold, the first condition will ensure that that manifold has an action of replica symmetry. But the question is whether that replica symmetry extends to the leading bulk solution that fills in this manifold. The leading bulk solution B that fills in with this manifold. This condition is much more non-trivial and requires geometric analysis, and that is kind of the main point of our work. And once you have this condition satisfied, then you can go ahead and take this bulk solution, push it back the replica symmetry R, and produce the orthogonal geometry region. So as I said, the first condition can be satisfied by any replica symmetry. You can find invariants that so that the replica symmetry R acts freely or constantly on those for any replica symmetry R. And the second condition is not immediately imposed. When the second condition is satisfied, we say that the replica symmetry is preserved in the bulk. When it is not, we say that the bulk replica symmetry is broken. Okay, any questions on this general operator? Now, one more point. The question of whether the bulk replica symmetry is preserved or broken not only depends on the multipartite invariant that we are going to compute, but it also depends on the configuration of boundary regions. It may be that you have divided boundary into A, B, C, D intervals, let's say. When A and C are small, the replica symmetry might be preserved, but as they become big and B and D become small, the replica symmetry might be broken. So such things are possible. So you can ask two types of questions. One is that given a particular configuration of the boundary regions, which multipartite invariants or multi-invariants in short preserve bulk replica symmetry. And second, what are the multipartite invariants that preserve replica symmetry, bulk replica symmetry for any configuration of boundary regions? We will answer both these questions. Okay. So let's say all these conditions are met. We go ahead and construct this replicative manifold M. We fill that in with this bulk leading saddle B. The replica symmetry that acts on M freely and transitively extends into this saddle B, and we quotient. After quotienting, as I said, by construction, the boundary goes back to being the original sphere. What happens into the bulk? I said there will be singularities. So let me just say what those singularities look like. So what you get is a triangle network of singularities, okay, and each edge of this network, you label it by the order of the group element that fixes this edge. So in this case, in the previous case, if I were to label that edge, I would call it M because it's the Zn element that fixes it. Okay, but you can have different orders fixing such singularities. So some examples are given here. So it turns out that the junction that is allowed for such triangle networks is of a very specific type. So in this case, you see a junction of the type 2, 3, 4. In this case, you see junctions of the type 2, 2, 3, 2, 2, 8, 2, 2, 6, 2, 2, 6, 2, 2, 3, and so on. So there are certain specific types of junctions that are allowed, and I will describe why that is also.
So 3 lines in the left diagram, like one line is by Z2, one by Z3, one by Z4, is that?
That's right. So the angle around each of the singularity then is 2 pi by n. So when I say that it is fixed under Z in the element, that also means that the angle around it is 2 pi by n. That's an 2 pi by n type singularity.
I say, wouldn't the curvature also meet point?
Nothing else. It's not curvature. So if you are very, very close to it, it just looks hyperbolic. It's no problem.
But if you have a conical singularity with a delta function and curvature.
Yeah, so some sort of delta function. But it is the point is that it is just obtained by quotienting the smooth surface.
That is fine. I'm just wondering if you would, is there a application to curvature?
No. Okay. Now, if if that is clear, let me, well, it should not be clear because I didn't mention it. I didn't explain why it works like that. That I can do it. So yes.
I can say about why the curvature is relative. So for example, in downstream computation of training entropy, the sort of area bit comes from the fact that there is a delta function curvature at the
Yeah, there is. There is. Of course there is.
So depending on, so would there be some sort of junction contribution to the final partition function or the junction?
It's just the volume, you have a bunch of volume, you're dividing by n, and instead of computing the full volume, you just want to compute the volume over final object.
Sorry.
Yeah.
At these junctions, do you have an overflow or some sort of kind of?
Yeah, there is an overflow. Yeah. Non-linear overflow that fixes that point. So this edge, for example, is invariant under Z2, this edge is invariant at Z3, this is Z4. And this middle point is invariant under a group generated by this, which is a non-linear.
So you're saying that because it's an object code, you have to anyway add a term that cancels that curvature. So
Can you add what?
a term to the action that cancels that curvature singularity.
Oh, you have to add a term to the action?
I think in Brown's computation you did after because otherwise you get two contributions from the.
Yeah, I mean, there are various ways people like to know this. I'm not sure what you
There's like some given fucking term. You have to add a given fucking term for the orbital, right? Why?
So for example, in the linear entropy calculation, you have to add a cosmic brain term because the genuine standard does not have a singularity, but the orbital does. You add a cosmic brain to cancel that.
Yeah, you put some matter that is supported on this, so that an engineer that singularity by singularity is supported on that.
Yeah.
Only on the singularity. Yeah, you can do that. That's a way to construct these solutions. So in that case, you just have what is delta function sources coming in and meeting. That is enough to construct this solution.
But you have to remind that the UV complete theory, whatever it is, that gravity theory, that actually admits this orbital singularities as valid configurations.
Yeah. I suppose you would have to demand it the way you would also for the Zn singularity. Just for the Zn singularity, you would have to admit. I mean, you have to impose that. Even that is admitted as a solution by the.
I mean, if it gets resolved, the action will not change much, right? If you resolve the orbital singularity, it's not like you expect the
But as long as in the UV complete theory, you can resolve it.
presumably. Yeah, this.
But not all orbital singularities can be resolved.
So you mean there might be some reason to exclude the this bulk solution because it cannot be resolved?
Yeah, I mean, like if you are not using string theory, but that's normal, some other theory, maybe it doesn't have all the resolution of the orbital system. Even Zn. In string theory, Zn can be resolved.
Even Zn.
Yeah. In string theory, Zn I think is an allowed orbital singularity. Maybe it cannot be resolved, but in the sense there may not be massless force that resolves it.
Yeah.
But you can define string propagation in that manner.
Yeah, I think in the same way you could define it because after all it's just coming from an object. I'm not sure. I mean, I feel that it's the same type as Zn singularity.
But these are semi-direct products. These aren't. You said these are non-abelian groups. So these
Non-abelian.
are semi-direct products of these Z's.
Yeah, you can think of them as
And so these delta function sources, you said they vary. On the boundary, there's no place for these sources to end. Right? You have not added these sources on the boundary. On the boundary, you just add.
yeah.
So in the bulk, what is the justification for adding these sources? You should just.
Well, I mean, all these things you could also ask for the Renyi entropy, for example.
Yes, you could ask for.
Yeah. So in that case, you could also have a source in the boundary, but it's y equivalent. If you have a conical deficit, it's y equivalent close to the solution. So in that sense, it's a matter of choosing a particular cutoff, so that you don't see that similarity on the boundary. So the boundary itself is a sphere, but in the bulk you have a similarity. Yeah, I would love to chat more about whether a string theory would admit a similarity. But at least at this level, at least I'm just looking at that.
At the classical level, there's a problem, but the question is whether, in principle, you can do systematic quantum corrections to this.
Yeah, so I have to kind of first of all see what sort of conditions I would think about that I have not thought about. So, yeah, you can talk about that.
These overfolds, they break supersymmetry, is that?
Yeah, there's no supersymmetry to begin with. Just a non-supersymmetric hyperbolic space. Okay. Okay, so as I was saying, so now let me just switch gears and go back to the kind of multi-part invariants that I have in mind that you can construct from one multi-part. The bipartite state, one is familiar with invariants that are constructed from and power to the density here and analytic continuations thereof. In the bipartite case, that is the only thing you can do. The bipartite state, that's the only kind of invariant that you can compute. And you can think of that as the reason why it is local invariant and local utilities is that you start with the state psi, and as I written down, you contract all the indices. And once you contract all the indices, clearly the object that you get will be invariant under local utility transformations. So in the same way, we construct multi-partite invariants by taking multiple copies of state psi and psi bar and contracting their indices. So all the party A indices of psi are contracted with all the party A indices of psi and psi bar. Same for B, same for C. Okay? But unlike in 2 dimensions, the way you could do that grows extremely fast, super exponentially, as you increase the number of copies, number of replicas. Okay? So I have given some explicit index contractions here. So I have here a 3-part state psi ijk, and the subscripts to the ijk is label which replica they stand for. And here you can see that J1K1 is contracted to J1K1 here, J2K2 is contracted to J2K2 here, J3K3 is contracted to J3K3 here, and the I is contracted in a secular fashion. So even though this is a tripartite state, the index contraction makes it so that it simply is trace of weight Q, because the party B and C has been treated in the same way. So these invariants are basically not distinguishing party B and C and thinking of the party B and C as the same party. That's because the indices for B and indices for B, C do the same thing. Okay. So even though you kind of write it in terms of 3 indices, you end up computing a bipartite quantity. This here is a different example where party A does its own thing, party B does its own thing, party C does its own thing, as you can see from these sequence contractions. Okay, and because no 2 indices can be just grouped together, these in some sense is a genuine multi-partite invariant. Okay. Just to emphasize this point, let me say that sometimes people like to construct multi-partite invariants by taking entropies, entanglement entropies, any entropies, their products, and their sums. But those, let me emphasize, are not multi-partite invariants. That's because you can find states which have the same entanglement spectrum across any bipartition. So any sort of quantity that you would construct from the range entropies would be the same for those states. But those states themselves are not equivalent up to local unit transformations. So such quantities that you construct by taking Renyi entropies of various regions and summing and subtracting them or adding them will not distinguish 2 states that are not equivalent to local unit transformations. However, if you start computing these quantities, they will give you different answers, and then it will make it clear that the states are different.
Would this same system apply also to the reflected entropy?
Reflected entropy. Okay. So as you can see, if you want to kind of systematically develop this theory of such multi-partite contractions, which we call multi-invariants, and taking more and more copies, if you just keep on writing with these index notation, it will become cumbersome very quickly. So we introduce a graphical way to denote these contractions. So we denote psi ijk as a white vertex with three arrows, three edges coming out, with different color I, j, and k. You could think of them as party A, party B, and party C indices. Similarly, psi bar, that I denote as a black vertex, and we also have these arrows, psi bar ijk. And then the contraction simply means that you just take the blue arrow from psi. So in order to construct this, you take multiple copies of psi, multiple copies of psi bar, and just join the blue lines from psi to blue lines to psi, blue lines of psi bar, and same with the red and the yellow ones. But you could do it in any which way you want. So in this case, I have denoted trace rho a cube. So you see that the green and the red, they go together in all, and the blue is a blue cyclic thing. So in this sense, it is a bipartite entanglement trace rho a cube. While this I2, if you denote it with this graphical notation, then it will be a graph of this sort. Note that this graph that you get out of this will always be bipartite. The connections will always be between black and white vertices. Cosine psi bar. Okay? So this is going to be the graphical notation that would be convenient to describe multipartite invariants, multi-invariants. Now,
how can like the diagrammatic classification where we can clearly distinguish which are genuinely complicated tripartite?
yeah, so it turns out that generically it would be multipartite. Right? The only case, only when the parties are treated, but different parties are treated in the same way, it becomes bipartite or one less partite. That means the pair of those edges should just always go together. But in the generic graph, that will not happen. So here, for example, only because these two lines go together everywhere, even at one point if they did not go, then it would be in some sense multipartite. But if they go everywhere the same way, then it's bipartite. It doesn't distinguish red and blue. You might as well combine them into purple. Okay. Now, such an invariant admits a description in terms of permutation tuple. So, what you can do is you can arrange all the size, n size here like that, and n psi bars here like that, and then you are, as I said, gluing the white arrows, joining white dots to black dots with various colors. So, for blue color, you have to give me a permutation element that tells me where to put this one, where to put this one. But in this case, I have picked this to be identity, so one just goes to 1, 2 goes to 2, 3 goes to 3. Now for the red color, you have to give me another permutation element. So here it's 1 goes to 2, 2 to 3, 3 to 1. So where is the red one? So 1, 2, you can see, okay, and so on. So if you have permutation elements associated to every party, then you can glue it this way and construct multi-invariant. But this labeling using the permutation element is not unique. There is a gauge freedom associated with that. You can take these permutation elements and multiply either from the left or from the right by a fixed number, a fixed element. Then you will get the same, because that amounts to just permuting, just a relabeling of these black vertices or white vertices. So you always have this gauge redundancy where sigma 1, sigma 2, sigma 3 is isomorphic to sigma 1 dot h, sigma 2 dot h, sigma 3 dot h. From right or from the left. You just have this isomorphic. Because that corresponds, as I said, to relabeling.
So, fixing one of them to be the identity.
Yeah, that makes sense. Okay. So now, once we have this type of description of a multi-invariant, it's clear what to do if you want to compute this in a quantitative area. Let's say 2D. So you take for each white vertex southern hemispheres, and for each of these arrows you have the regions. So there is a blue region, a red region, and green region. They correspond to these indices, each of them. Similarly for black dots, you have these n copies of the northern hemisphere, the region decomposition. And the way these gluings are denoted in the graph, you just follow the same gluing for the regions. So here the blue is contracted like this. You just take this region and glue it to this region, this region, this region. with identity. Now the red of this is contracted with the red of that. So you take this region and do it here. So it will lead to a complicated gluing on the manifold. And finally, once you connect all these things, you will get a space which will not have any boundaries anymore. It will be a compact space. Of course, it is going to have conical axis angles at various points. Okay, but that doesn't bother us too much because we know that you can always uniformize it. Now, so in general, if you do such a gluing, you will get some homogeneous surface. You will get some homogeneous surface, and the genus of that surface can be read off from this combinatorial data using the Mandelstam formula. Let me not go into the details of that. Moreover, once you get this replicated surface, you can see where the ingredients that you use to make the surface sit. So, because this is a hemisphere with 3 boundaries, it will tessellate with triangles, white triangles and black triangles. So you will get a homogeneous surface tessellated by white triangles and black triangles. Okay? And if you had multiple regions, n regions, let's say, they will be tessellated by black n-gons and white n-gons. So you should always try to find that tessellating pattern on the replication surface that you get. Now, as I said, if you are interested in computing this partition, this invariant for this vacuum state, you want to compute the path integral on this replicated manifold M. Now, in general, it's a difficult task, but when the theory is holographic, you can compute it using geometric dual description, where you take this replicated manifold M, find the bulk solution that fills this in, and compute E2 minus SP gravitation. Now, this measure E, this invariant, E has symmetry G that acts freely and transitively on the replicas, then M modulo G is the original manifold S2. Okay. If the replica symmetry is also enjoyed by the bulk solution, then we quotient the whole thing by G, not just the boundary. Then because M by G is S2, we get a hyperbolic geometry whose boundary is S2 with possible conical singularities in each area. And the conical singularities appear because the action of G on B may have fixed points as I mentioned. Okay, so this motivates the construction of multi-part invariants with the replica symmetry that acts freely and transitively on the replicas. This does not guarantee B is a replica symmetric if it does not preserve bulk. So for example, this E2 example that I gave, it does not preserve bulk replicas. Okay, so before we move on to discuss the bulk replica symmetry, let us first address the condition 1 that I said, where I require that the replica symmetry should act freely and transitively on the replicas, on all the replicas. Not if this extended to bulk, that we will look at later. And this condition is very easy to solve. You simply do the following. You take, let's say you are interested in having G, some group G as the replica symmetry. What you do is you take multiple copies, in fact G worth of copies. You think of G as a set and take copies which are labeled by the group elements G. Okay? So those are your replicas. So those you have size and also psi bars. And then each of these replicas are assigned group element A. So each of these replicas is assigned, let's say H, group element H as its label. And now for every party we associate a generated GA of the group. So we connect a bra with a ket only if they are related by the GA action, like this. So H the bra is connected to GA.H ket with the action of GA. So this connection will be for the party A. Okay, so I'm using this group action itself to construct these permutation elements that connect the parties. Okay, and this is with the left multiplication. Alright, multiplication. So the advantage of this is that the group action on the replicas by left multiplication commutes with the right action and hence gives rise to the replicas. In fact, if you are familiar with the Cayley graphs, this is nothing but a construction of the Cayley graph. And then once you have the KT graph, which is constructed by the left action, then the right action is an automorphism of the KT graph. So this is the replica symmetry that the multi-invariant enjoys. Okay. So in this way, for any replica symmetry, you can construct an invariant on which the replica symmetry acts freely and transitively along the replicas. And we further, of course, need to specify generated G for each party for such construction. Okay, now let's go back and now let's go ahead and look at the second condition. In what cases this second condition could be satisfied? So let's say you construct this replicated manifold after doing in various ways, and this replicated manifold is could have any genus. So we will start with genus 0. So let's say this replicated manifold has genus 0. So it is filled in by just some hyperbolic ball. You can take that genus 0 surface to be just a sphere, and it is filled in by the hyperbolic ball. So you just have hyperbolic space, the standard hyperbolic space. Okay, and you want some replica symmetric group acting on this. And because you want to act on the hyperbolic space, so that you want to quotient it, it should be an isometry of the hyperbolic space. The isometry of the hyperbolic space, we know it is SO3, 1. So what we are looking for are finite subgroups of SO3, 1. It turns out that the finite subgroups of SO3, 1 are the finite subgroups of SO3. So 1 doesn't play a role if you want finite subgroups. And finite subgroups of SO3 are familiar. They are symmetric of Platonic solids. Okay? And so I just given the Platonic solids, and their symmetric groups can be understood. But an instructive way to look at these symmetries is by looking at the fundamental domain of the symmetry action on the sphere. So this is how it looks. It gives you, as promised, the tessellations of the sphere by white triangle and the black triangle, white triangle and black triangle. So, and each of them, I have a label which denotes the order of the fixed points. So, for example, in this picture, you can see. Let's take this white triangle. Let's look at these corners. So there is a two-fold symmetry. That's the 2. Here there is a 3-fold symmetry. That's the 3. Here there's a 4-fold symmetry. That's the 4. Okay. So this tells us a convenient way to label the symmetries that are acting on the sphere. And now once you have that, note that this extends also into the bulk. So you can think of this tessellating, extending all the way to the bulk to the origin, where the origin becomes fixed point of all of them, which is what is going to give rise to the junction point. So once you have that and you quotient this whole thing, this is the picture that you get. You get a trivalent network of singularities, which is labeled precisely by the numbers that appeared earlier. So in this case, the case that I explained, you have 2, 3, 4. So one singularity would be of angle 2 pi by 2, 2 pi by 3, and 2 pi by 4, and then the junction at the origin. So this is the structure of the orbifold that you will get after quotienting this geometry, this hyperbolic space by the symmetric groups of Platonic solids. And note that the junction that you get from this quotienting is of very specific type, because there are not infinitely many Platonic the Platonic solids in 3 dimensions that we understand them, what they are, and you cannot just have any numbers that you want. They have to be, they have to have this pattern. You can understand this from the point of Coxeter groups also. And for a Coxeter group to be finite, it needs to satisfy various conditions which are summarized conveniently in Dickin diagrams. Let me not go too much into detail about that. So the kind of junctions that are admissible are 2, 2n, 2, 3, 3, 2, 3, 4, and 2, 3, 5. Okay, so let's remember this point about the junctions. And once you have that, you can reverse engineer the invariant, which after carrying the flowing out will give rise to this surface. That can be just read off from the kind of tessellations you have or the kind of symmetry action you have. Okay, so in this case it becomes this. The symmetric group is Z2 times Z2, or the second item, which is Z2. Okay, good. So now let's move on to the non-trivial problem, more non-trivial problem. What if this replicated manifold has higher genus? How will we ensure that the symmetry that this manifold has is also enjoyed by the handle body that is in the same? The handle body, because that's the dominant gravitational solution, and we want the symmetry also to act on the handle body. Okay. So in order to understand that, it turns out to understand the handle bodies themselves first as the quotient of hyperbolic space. Okay. And then we will see how we can construct symmetric handle bodies so that we can quotient them or obtain these order quotients. Now there is a very nice construction of handle bodies using what are called Schottky groups acting on hyperbolic spaces. So let me quickly, I don't have much time, so let me just quickly say what this type of Schottky construction is. So on the sphere, so take for example just a sphere bounding the hyperbolic space, a three-dimensional hyperbolic space, and on that sphere draw G pairs of circles. So this is one pair, this is another pair, and there could be multiple pairs for that. Okay. Construct a conformal transformation that maps one circle of the pair to the other circle of the pair. So this would be like a scale transformation or scale interrotation together and so on. So construct these transformations. So you will have G transformations and consider the group generated by these G transformations. And this is going to be a free group on G generators. Okay. And this group this group, of course, because it's a conformal transformation, it's a group that is a free group and it's a subgroup of SO3,1. So you go ahead and quotient this boundary, let's say, to begin with. What that does, it removes the interior of these circles and just glues one boundary, one pair of the circle to the other pair of the circle, creating a handle. So in this case, you will create G handles giving you a G and G circles. Okay, and what is nice is that this can be extended all the way into the bulk, and the construction involves scooping out ice cream kind of a scoop here from the hyperbolic space from here also, and then identify that both these boundaries are going to have zero vanishing, zero extrinsic curvature, and then you can glue that, and this gluing, if you carry this out, it will produce the genus G handle body that is filling in the genus G Riemann surface. Okay, so this is the Schottky construction of the handle bodies. Okay, so first we understand the handle body itself as this Schottky quotient, which is a group, free group on G generators acting on the hyperbolic space, a subgroup of SO3,1. Okay. Okay. Now let me just quickly outline the idea. So without motivating, let's first consider a discrete subgroup K. It is going to be an infinite subgroup K of the bulk isometry group, and I want this K to satisfy the property that it has a free normal subgroup SG with G generators that is a finite index, meaning K by SG, which is R, is a finite group. That's the kind of group that I'm looking at. Okay, because it's a subgroup of SO3,1, it's called a Kleinian group. Okay, and it is a normal subgroup, it has a free normal subgroup, the finite index. That's why it's called virtually free. So what we are looking at are virtually free Kleinian groups. That's the kind of group I'm interested in. Why is that? Now it's very easy to construct the handle bodies that are symmetric, which we can use to quotient. So consider the hyperbolic space divided by the Kleinian group, virtually free Kleinian group. Now this quotient, if you do, you will get something, some orbifold. But it is useful for us to think of this quotient in two steps. First, you quotient by the normal subgroup SG that lives in K. Okay, and once you do that, we already discussed this is a Schottky quotient and gives you a genus G handle body. But this quotient does not exhaust all the symmetries because K by S symmetry, which is R, the remaining symmetry if you wish, that is still there. And that symmetry now acts on the handle body that you got after quotienting H3 by G. And this is exactly the kind of thing that you were after. One was after the handle body which are symmetric. And now once you have that, you can go ahead and quotient the handle body by this remaining group and give you this orbifold V tilde. But note that even though it is expressed like this, at the end of the day it is just this H3 modulo K, where K is the virtually Kleinian group. Okay, and this construction has an interesting upshot. It gives you multiple multi-invariants that have the same dual description, same gravitational description. Okay, and as a result, you get infinitely many qualities between multi-invariants that a gravitational state or holographic state has to satisfy. Okay, so the idea is this. So you have H3 and you quotient that by K to obtain this orbifold B tilde. But you can do it in steps, as I said. You can quotient by S1, so a free group with a bunch of generators to get this Riemann surface with genus G1, and then you can quotient by the remaining symmetry to get to this. Or you can use a different, so it turns out that if you have a virtually free group and you find a free normals of them, infinitely many free normals of groups. So you can use any of them to quotient, and you get Riemann surfaces with a different genera. With the property that once or handle bodies with different genera, with the property that when you quotient by the remaining group, you finally end up with the same one. Okay, so in that sense, different quotients, for as far as our invariant is concerned, it only accesses this part. It just starts with some handle body, and then you quotient by this replica symmetry. So you can see that there are infinitely many invariants that after quotienting reduces the same orbifold. So that means that there are infinitely many multipartite invariants which give you the same geometric description. As a result, there are infinitely many equalities that the multipartite state has to satisfy. In that sense, the holographic states are special. In the beginning, I asked this question: in what sense the holographic state is special? This is the sense in which they are special. There are infinitely many equalities that they have to satisfy. A generic multipartite state definitely does not have to satisfy. Okay. So this establishes the importance of what I call virtually free Kleinian groups, and there are various ways of constructing that. In particular, there is a beautiful mathematical tool called Klein-Masket recombination, which takes the Kleinian groups that exist and then can combine them together to find a new virtually free Kleinian group. So in the beginning, we started off with finite Kleinian groups. They were given by this type of junction condition, and you can think of this being its fundamental region, and you can take one more of that, and there's another fundamental region which stretches off to infinity, and the Klein-Masket theorem says that under certain conditions, the intersection of the fundamental domains forms the new fundamental domain for a new group. Okay? And this is going to be an infinite group, and that's the virtually free Kleinian, or one of the virtually free Kleinian groups. You can construct this virtually free Kleinian groups in this combining the Kleinian groups that you already know, namely the finite Kleinian groups that you already know. And at the level of the orbifolds, what happens is that this finite Kleinian group gave us this singular structure and this singular structure, and this amalgamation gives us connection between the two, and it ends up constructing this type of network of singularities. And then once we have that, you can successively combine more and more to give you any sort of singularity that you are in. That you can imagine, but the only condition that they have to satisfy is that at every junction, the junction has to be admissible, meaning it has to look like 2n, 2 3, 2 4, 5. Okay. Now, as I said, the question of replica symmetry also depends on the configuration of the regions. So, for example, here I have taken A to be small and this part to be small. That's why this stretches it. But let's say this part and this part become small, then you would have an S channel going to T channel type of transition, and in that case, it is not clear what will happen with the replica symmetry. So if you ensure that even after the transition, there is an admissible assignment to those edges, then you can construct the invariant, which even in that chamber will preserve replica symmetry. So this tells us that. So I talked about the construction of multi-invariants based on a group. If that group were a finite Coxeter group, then it turns out that for any configuration of these external regions, at least in every corner of those configuration space, you have a replica symmetry that is preserved, and you get this type of network after quotient. Okay, so and one thing I should mention, so these ideas, we checked those ideas for genus 0 case and in some cases for genus 1 case in conform explicit computation conform field theory, and we saw an explicit match between the bulk prediction and the CFT prediction. And interestingly, these Coxeter invariants also made an appearance in our earlier work where we classified multi-invariants that are entanglement monotones. So we asked a question that's totally different from the question that we are asking. We asked what are the invariants that have monotonic properties under what I call local operation classical communication, and the answer to that also turned out to be these Coxeter invariants. So it's a very interesting, these seem to have very interesting properties. So useful to explore this connection, why that is the case. And various ideas, the ideas that I mentioned also generalize to higher dimension. But this, in the beginning, I assumed that the geometry with the conical axes is y equivalent to a geometry without them. Can uniformize that, uniformize the surface. In other words, this feature, although was not directly used, was used to say that the symmetry that acts in uniformized picture, it also acts in non-uniformized picture, and then the higher dimensions, this correspondence is not there. So that's why you cannot try to go back and forth. Although I do feel that with certain modifications, these arguments also should hold in higher dimensions. Also, one more point is that because these are computed by saddle point, only saddle point nature is being used. So if you have higher order connections, higher derivative corrections, or stringy corrections, modulo the fact that to see whether those singularities are admitted by a string theory, it would look like if they do, then these equalities are robust even against those stringy corrections. So it would be interesting to check these equalities for large and vector models or large and symmetric product problems. Okay, I'll stop it. Sorry for the more. Thank you.
Questions? Okay, multiple questions. So, first of all, you say that so your results are compared against high derivative corrections. And when you're explicitly using the geometry of hyperbolic space here, but then anytime you have any corrections to GR, like even a scalar matter, wouldn't
well, I'm assuming that the hyperbolic space is admitted as a solution. Yes. They were the theories.
So, but like for example, if your state has, if your state has a matrix excitation, then
That's up to state.
That's
Right?
huh?
matter excitation.
Yes.
No, I'm looking at vacuum state or what are called the holographic state.
Okay, so you're like
We
looking
talk
at
about holographic states. It's a state which admits a semi-classical description.
Holographic states can have matter excitation.
Yeah, I mean they have to be heavy enough. Yeah.
certainly, but like yeah, so I'm wondering, like I would agree that your construction theory works for all dissonance of identity, but then you could have like if you have like some light operates in the spectrum, then is it clear that there are descendants of those light operators. Does it also work for that?
As I said at the beginning, I was looking at the vacuum state. That's the main application. Or to states where you excite the vacuum with heavy operators, which you can model by some geodesic propagation of the current, or from moving double states in such states. Now, the light matter excitations, one has to do.
So light matter excitations can't you consider by doing QFT in curved space-time? By considering the background is whatever it is and
Yeah, but the quotienting doesn't quite work there because the fluctuations need not have the Zn symmetry that you are quotienting. Only when there is a saddle point which is symmetric, you can quotient and read off the saddle point action, which is 1/n times the original saddle point action. But if there are fluctuations, this quotienting, if you were to do, it will make sense only for the Zn invariant fluctuations. But a priori fluctuations will be,
I see.
may not obey that.
I see. And if you have some excitation, then if that's modeled by geodesic, why is it important it should be modeled by geodesic?
Because then you can just use saddle point completely.
But what about the Zn invariants that you just explained for excitations? That would also be a
No, there is no excitation. There is actual geodesic particle moving through the bubble.
Like the conical similarity states?
Not conical, it doesn't have to backly act. It would just be heavy compared to order 1. So that I can use it as a geodesic. Yes.
Can you have sort of disconnected graphs, but are those maybe trivial in the
Yes,
sense that
that's
don't give
possible. Yeah.
you invariants?
Yeah. And in fact, if there is an interesting topology, then there could be a loop also, which is a homology to that genus.
and if it does back react, you will not be able to preserve that.
No, even then, back reaction is not a problem, just the quantum fluctuation. Back reaction, I think, because in 3 dimensions, back reactions are not that problematic. The space is still locally hyperbolic. The back reactions only makes it have a conical deficit.
So like it's not classical point matrix, like classical field.
But okay, that requires some thinking. Back reacts are
Yeah, some compact
but I just feel that the
extensions
space is a hyperbolic.
So if you have some compact extra dimensions and so on, that is not precisely correct.
So all that is just going away from the kind of assumptions that I was making. In higher dimension, I think, it's not so straightforward. Yes.
These equalities that these multi-invariants have to satisfy their relation with these entropy cone inequalities.
So there, entropy cone, as far as I know, where people compute entanglement entropies, you consider a bunch of regions, compute entanglement entropies, and see that there are various inequalities that they satisfy, which follow from the Hamilton formula. But 2 points. One is that they are inequalities, right? So they don't end up necessarily kind of restricting the state to a subspace, but rather to some cone, right? The dimensionality that you explore is still full. And the second, it doesn't probe the multipartite structure in the sense that I was talking about, because it is just a sums and differences of the entanglement group. And you could certainly find multipartite states with equal spectrum. So in particular, that would mean all Rayleigh entropies or multi-entanglement ones, but the states themselves are not unity equivalent. And then here you get equality, so in that sense, subspace reduces that the space can be spread. Yeah.
Actually, just related to this question, so these multipartite measures will give you some refinement of the holographic entanglement or the holographic entropy code, right? Because that is trying to place some necessary conditions on what states are all holographic, and this will give you some refinement of that. But so
But I just mentioned the differences that I have in mind.
you have different, but I'm just saying that whatever states you get, I thought the motivation of holographic entropy cone was to classify these states as holographic, like you see. So the point is there, why don't they have to worry about this issue of, if you add quantum corrections, because even when you usually derive the formula for the entanglement entropy, you assume this replica situation.
Yeah.
But when they take into account these quantum corrections,
Quantum corrections, what helps control those is the fact that you are taking n going to 1 limit, so that the singularity approaches the flat metric there. There, you can, in fact, that's the way in the beginning of the Mandelstam was.
I see.
They kind of argue that the entanglement entropy is the same as the area term plus bulk entanglement, but it uses this fact that the singularity flattens out in the end. So here, all this orbifold structure is very rigid. There is one case where the edge can have n on it. That n you can do anything you want. But the other edges have very specific labels, 2, 3, 4, and so on. You cannot take those.
Let's take Abhijit.